Hello, everyone. I'd like to welcome everyone back from lunch for our session on stability and reproducibility in data science. We've got a great lineup of speakers, the first of which I'm pleased to introduce is Professor Kedron. He describes himself as a human geographer and GIS scientist. He's an associate professor of geography at the University of California, Santa Barbara, but he has an extremely multidisciplinary background in economics and psychology as well as geography, and today, of course, he'll be talking about data science. His recent work focuses on evaluating not only what policies work, but where they work. Please give a warm welcome to Professor Kedron.
Thank you, everyone, and thank you for that kind introduction. I'm very excited to be here, as all of our previous speakers. Many of the people I've been reading for many years are in the audience, and that's always an exciting position to be in, to talk about how their work has influenced yours, and hopefully your work can influence theirs in the future. I think to get right to it, let me just go to my central message of the day, and it's kind of an overarching one. I've been trying to think of ways to build bridges between the idea of veridical data science, as was presented this morning, and what we've been developing in geography and spatial statistics. And so kind of at the highest level of my talk here, my kind of central message today is essentially I think that adopting a spatial perspective or a spatial approach to problem solving, where appropriate, if you're analyzing biological data, this may not be the best way to do it, can enhance the reliability of the approach that we've been talking about today and actually improve stability and predictability and ultimately problem solving. Now, I know that some of you in the audience may be a little bit less familiar with a spatial approach or a spatial perspective, but essentially what I'm saying there is to think about the way in which the processes you're exploring unfold spatially, across space, across geographies, across contexts. And although you may not think about it this way, if you've ever analyzed social or environmental data, you probably have dealt with spatial data because most large data in that can be tied to location and is in fact spatial. And this is actually a very good thing for all of us in many ways, because spatial data and the spatial support allows us to integrate data and information from many different disciplines, many different perspectives to bring to leverage on problems. So this is one of the key values of spatial data, is that it allows us to have this kind of layering perspective on different forms of data, bring it together in the form of a map that allows us to analyze problems from this very multi-dimensional perspective in the real world. Now, the one challenge with this is that when we do have data that is spatial, we often end up in situations like on the far right, where we're violating fundamental assumptions of statistics, in particular assumptions of independence of observations. So when we have spatial processes, particularly we may have spatial non-stationarities, we may have spatial dependencies, and these may create directional or anisotropic effects in our data. So for example, if you're modeling wildfires in California, you may have different soil types producing different types of vegetation that create different risks for burning. You may have directional effects like you may have spillover effects like fire hopping from tree to tree or hopping from tree to building. And you may have directional effects based on our building of patterns along canyons and things like this. And these are all things we want to consider when we're building our models, trying to come up with ways to analyze this data. But on the plus side of things, for the last 40 to 50 years, we've been progressively developing both data handling frameworks in geographic information science and data analysis frameworks in spatial statistics to deal with exactly these kinds of data and exactly these kinds of dependencies and leverage them to our advantage. So that's been wonderful. We have a really good foundational set of knowledge to build forward on. But one of the challenges we face is kind of echoing many of the things that have been brought up throughout this morning, is that we've continually built those techniques, but not thought about how we actually employ them, how we actually leverage them to solve problems. And so what my kind of recent work has been doing is trying to introduce some of the techniques that were talked about today and build into geography, and to build a culture in my own discipline around the idea of replication, reproduction, and these idea of veridical data science. And so these are some very simple toy examples that I brought into the field a few years ago. In geography right now, in spatial data science, we don't really do very much specification curve analysis. We don't look at the stability of our findings to alternative specifications. And in this case, we can see that the choices we make on some of those spatial parameters can actually affect our estimates quite a bit. Or even in a simple sense, we don't look at predictability of taking a model developed in one location and seeing how much it holds up to explain in another location. This is just a simple example on the right of a COVID-19 model that was created in New York City reproduced and replicated in Phoenix, and showing some instability in some of those parameters. So I think at the highest level here, we've kind of been developing these frameworks, trying to create this infrastructure change, this culture change in our discipline. But what I want to talk about today in this audience in particular is some of the ways I think the insights from geography and spatial data science and connect with the vertical data science framework, and how we might create a walk back, a conversation back and forth between these approaches. And really I want to hit on three major overarching ideas, playing on the ideas of stability and predictability from this morning, and then adding a different C, in this case context, but could be very much tied to domain knowledge. So on the stability front, I just want to say that decisions about how we represent these spatial processes and handle spatial data can destabilize results to the same degree that we see some of the other decisions we've talked about destabilizing our results. But I don't see in a lot of data science work the spatial aspects of the parameterization, the setup of design, all these kind of things really emphasized in many cases. So I think that's a place where we can make connections. I also think on the predictability front, we often don't think about changing our data as changing locations. And when we change locations, we change context, we change the environment we're working in, and that may have radical effects on our predictability across locations, not just across data sets. And then finally, I think a key sort of general insight from geography is a very close attention to context in which we do our analyses. Very similar to the discussions this morning of clinical context, we can think of regional context or location-based context as fundamentally changing potentially the systems that we're working in and leading to very different predictability levels in our results. So just to dive into these three a little bit in some degree, probably the most well-known example of a challenge to stability from a spatial perspective is what's called the modifiable area unit problem, which is essentially a change of support problem when you have to aggregate your data to some spatial aggregation, a region, a county, a census tract, and making that choice can radically change your outcomes, yeah? So this is essentially a spatial version of Simpson's paradox, where if you model data in one way or slice it up in a different way, you come up potentially with radically different results. And the MAUP is just one of many different spatial decisions that you can make along the way in your analysis process. It's probably the most well-known again, but choosing the extent of your study, choosing how you match data collected from different locations in terms of their semantics is important. How you're going to represent those spillover effects, those spatial non-stationarities that I talked about before in your model. And we do have guidance on these things in geography, but we have not yet really done robust analyses of how these things collectively together can drive our analysis in one way or another, affecting the stability of our results. Yeah? And so I think one way forward on this in particular was mentioned a couple times this morning, is to really pursue multi-analyst studies that pay attention to these spatial decisions very closely, because that's a way for us to observe the effect these decisions have on different analyses, and also potentially try to link some of the heterogeneity in our results to specific decisions. And so this is something I'm trying to set up right now, working with Esri, kind of one of your largest spatial analysis companies, or probably the world's largest. And I'm particularly interested in working with them because they create a lot of guidelines in their software for how to do applied spatial analyses that maybe people in our room here don't use as much, but all the people all over the world, like millions of users, actually use to do their spatial analyses and then make decisions about how we use our resources, how we do social policy, so forth and so on. And my real big concern about this is within that company and many other places, we're trying to develop AI assistants trained on the existing data we have, which probably suffers from the selection bias, publication bias issues that we had before. And if we train on those things, we're going to train to make the same mistakes we made in the past. Yeah? So we'll try to avoid that. And I will just say, thinking about these things in detail often lends itself to new insights. So this is a quick example from a paper that was published in Nature a year ago that we were trying to replicate. We were interested in just kind of teasing this out. It's about protected area conservation and the effect of protecting locations around the world has on biodiversity outcomes. We were playing with this paper, and we realized in here, they did a really kind of pretty cool job making a causal effect of protected area status on biodiversity outcomes, but they didn't consider a key secondary part of the driving kind of international programs that are pushing this, which is the 30 by 30 initiative, which says those protected areas should also be connected. The spatial linkages between those places are important for gene flows, migration patterns that will also affect biodiversity. So in doing this replication, we added in a small little spatial tweak, and we came up with this preliminary result that we're still testing the robustness of that suggests that there may actually be a moderating and amplifying effect of protected area status when you have a better connected network. So these are the kind of things that we can get in terms of policy implications carrying forward. So that's stability. I'll briefly switch over to talk about predictability. And so this is an example from work with my PhD student, Sarah Barden, where we're looking at the policy environment here. And essentially in federal policy, we often think of, to the speaker before lunch, we often think of these policies as having a single effect across the entire population. And so this is an example from the Teen Pregnancy Prevention Evidence Review, or the TIPPER database. This is one of 12 federal evidence clearinghouses where we basically collect together many large RCT experiments run over many years. This is about 30 years of pregnancy prevention interventions done throughout the United States. 3,000 impact findings, 200 evaluations run across 33 states. And the typical way we look at this is here on the left as one big effect size distribution, which we meta-analyze to get a single effect. And in this case of this database, we see essentially a slightly positive or zero effect across all these reviews everywhere. Now, the rub of this is if we think about this as a spatial problem, we may recognize that there isn't a single distribution here. There may be regional distributions driven by some contextual effects or cultural differences, things like this, that may actually hit that some of these interventions, abstinence-only comprehensive sex education, are differentially effective in different places. And so that's what we did in this quick little study here, is we took this database, created this spatial data for it, which I should say was not available beforehand. It's not recorded in these evidence databases, so we can't do spatial analysis. We had to rebuild this from scratch. Credit to my PhD student for doing that, to create these localized effect size estimates, which are here averaged at the state level. And you can see some geographic variation in how these programs appear to be effective in different places. I'll reserve that map at the top for questions later in case someone asks anything about that. And just to show you kind of bringing it over to the effect size scale, we can actually observe differences between states that are measurable in our big meta regression model of this data. So we can see differences between Texas, New York, Arizona, Massachusetts, and Ohio, and Texas and North Dakota. We chose Texas as a reference category here because it's a large, diverse state with a large school population where these interventions are often done. So if we want to explain this, we're observing some variation here potentially, but what's driven by it? And I think this brings to my last point here, is just the one about context. And I want to emphasize the way in which I think geography, GIS, this spatial statistics tradition can also contribute to vertical data science. We often think of data science as domain knowledge, computer science, and mathematics and statistics. All of these components are extremely important. But I would argue in geography, what we also pay attention to equivalently in domain knowledge is context knowledge. Knowledge of understanding very deeply how that place works, how that place functions, and what might mediate, moderate the effects that we expect to observe in that location. How should we build those regional variations into our analysis setup, into our stability checks, into our predictability checks, if you want to think about it in the VDS kind of language. So I think this is an important way to think about this, and at its best, in my opinion, spatial data science leans on what we call a specialist synthesis tradition, in which we develop a specialized knowledge or lean on domain knowledge of a particular problem to help ask the right question, set up the design the right way, as was discussed this morning, but then also have a capacity for vertical synthesis, bringing together a lot of information about that particular location, and also horizontal synthesis, thinking about the way in which that model may or may not translate to new locations. So I think this is a really important, crucial element that we can also bring in to vertical data science and have this conversation back and forth. So again, just to bring back to that central message, hopefully these are some of the ways that you will see, hopefully, that a spatial perspective, spatial approach can add value to the development of this emerging field, and we can work back and forth across these different disciplines to make those advances. And with that, I will open for questions and comments. And if you're interested in any of these particular pieces of information, a lot of the work that we've been doing on the infrastructure building side within geography is available with this OSF project or the GitHub organization, where we have 20 or 25 different replication studies in there. And then obviously I'm from the Center for Spatial Studies and Data Science at UCSB, and there's my website as well where you can find my papers. So feel free to grab any of those and I'll take any questions you have. Thank you very much.
We've got about 4 minutes for questions.
I did a great job.
Professor Kedron. Such a great job on the time. Any questions?
In the back?
Hey, thank you for the talk. I did development economics for many years, so this is really interesting to see how you think about it. I'm just curious, like the stability versus predictability across context. You also mentioned context, like what is the most productive approach? Because we know, for example, you might have heard study by Ava Vivald in like how development RCT trials. First of all, if we want to look at a program like even like you said, pregnancy prevention, there are many specific forms. And when we look at a sort of program that looks similar on the surface, you know, in Kenya and India, it's like very different. If you implement a small NGO or government, it's different. And a lot of times, like you said, this instability is almost like a feature, not a bug of the whole situation. And I don't know what you think about the most productive way to like deal with this. Is it to build, because you could say, oh, this model doesn't work somewhere else, but if you plug in the right parameter for that place, it works. Or if you add the third input, the hidden, I think Maya mentioned like modifier, then it would work now. So like, is it most productive to build like bigger structure model that encompasses all the potential modifier and contextual information, or is it just like more ad hoc? I don't know what your perspective.
Sure. Yeah. No, my perspective on this is actually maybe a little bit traditional, and it kind of actually mirrors, I think, what was said a couple times this morning. So I think conceptually answering that question, where I draw a lot of inspiration is the work of Nancy Cartwright, who has some really good books discussing essentially sort of like how the information you get from an RCT is really good potential evidence of efficacy, of effectiveness, but not efficacy of transfer across location. So in terms of thinking about how you want to think about a problem at a large level, that is a really good place to draw inspiration for design. I think on the practical design standpoint, I think it's less about throwing all the data at the problem as it is about having careful design, as was mentioned this morning earlier on. Specifically, I think they're leaning on mixed methods approaches that have a quantitative, qualitative component, really help build that design, particularly when the qualitative information gives you rich information about context. So in that pregnancy prevention example, for instance, those federal policy evaluations are done in these kind of RCT kind of setups, but they also are augmented with extensive survey data and interview data with teens in those different contexts that give us great insight into the cultural differences about when to initiate sex, when to have children in different regions of the country that help us explain why something like an abstinence-only policy, given in a culture where it's common to initiate sex at 13, 14, as opposed to one where it's common to initiate sex at 18, 19, would land radically differently. And so having that kind of information helps you both make sense of your results, but also design your study to kind of pull these things out. And I think, in my mind, that's kind of the best way to do this, is to really think through what you know about the system, what you know about the context, to deal with it. So thank you for the question. Yeah.
I think we have time for one more question.
In the corner over there.
I just came in with my mom. Can you like summarize what you stated? What's the most difficult part of your research?
That is a dazzlingly difficult question.
You have 20 seconds.
I have 20 seconds. The hardest part of my research. Yes, I think, again, this design element, right? So trying to figure out how to measure and think about context and how to fold it into the design of experiments, the design of replications, and the measurement of those things across locations. Because we know locations are going to be different. We know they have these structures, but they're quite difficult to uncover and then to include in models. So balancing that between what we know and incorporating it into the model on the front end or letting the model tell us is very difficult. And I think that is the hardest part that I have, is figuring out how to untangle that boondoggle, which maybe isn't so different from what other people would say in their own disciplines as well. So, but thank you for the question. My pleasure.
Okay, let's thank the speaker.